Hello everyone, my name is Elnur Elbarer and I'm a Field Applications Engineer with ST Microelectronics. This video is the third video in a three-part series explaining and demonstrating our new I-CUBE-ExpressLink pack. In this section, I'll be demonstrating how to use our Secure Boot project to deliver a host over-the-air update from AWS to our host microcontroller. This video does depend on some of the prerequisites accomplished in the previous videos in the series. If you haven't gone through the demonstrations in those videos, please take a look at the links in the description and make sure to follow along prior to following with this video. We'll be starting where we left off in the previous video. I currently have my STM32 microcontroller connected to AWS via the ExpressLink module. If we take a look at the ExpressLink directory, which is under this PC, C, users, your username, STM32 repository, packs, ST Microelectronics, and then I-CUBE-ExpressLink 1.00, projects, free RTOS, and then the board name that you'll be using. For this demonstration, you'll have to be using either the Nucleo G071RB or the BU585i IoT02A, as these two boards are the only ones compatible with Secure Boot as of the time of the release. In this video, we're using the Nucleo G071RB, and as you can see, I have my CUBE-MX project generated in CUBE-IDE, and if we take a look, you can see that here. I've also built the project within CUBE-IDE as we've seen in the previous video. If I take a look at TerraTerm and reset the board, you can see that the application is up and running on the STM32 and we're connected to AWS with application version 0.9.1. Something to keep in mind is that I am using the Nucleo G071RB, and this device is a single bank device. As we saw in the previous video, it is possible to deliver a host over-the-air update to devices in some cases at this point. Let's give it a try with this device. We can navigate back to our projects folder, and under scripts and then host OTA, we can open up the HOTA update PowerShell script in a text editor. We'll make sure to uncomment the board name that we'll be using, and then also verify that the rest of the environment variables are set correctly for our environment. If so, we can open a terminal in the directory, and just like we saw in the previous video, we can run the script by typing its name, HOTA_update.ps1, and clicking enter. As long as you have your AWS credentials and AWS CLI configured, you should deliver an update as we saw in the previous video. Now if we go back to TerraTerm, we'll see that a new host update is being proposed, and right now it's being downloaded to the ExpressLink module. The new image has arrived, but as this is a single bank device, we won't actually be able to run the new application version because we are not using the Secure Boot project. To enable the Secure Boot project, we'll have to go back into CUBE-MX. If we go under middlewares and software packs, and then I-CUBE-ExpressLink, and user constants, we'll see one user constant called Secure Boot. Double-click that user constant, and then set the constant value to 1. Next, click OK, and then OK again, and we'll have to regenerate the code. The code has been successfully generated, and if you already have the project open in CUBE IDE, you can click Close here. We can navigate back to CUBE IDE in order to make a few modifications to the FreeRTOS project. The first change is to update the flash memory origin and length. To do so, open up the STM32 G071RBTX flash.ld. The name of the linker file may change depending on which board you are using, but it will always be postfixed with the .ld file extension. There, you'll see a section called memory, and then within that section, you'll see a field called flash. To update the origin, we'll change the number to 8008200. And for the length, this is also dependent on the board that you're using, but in the README for the Secure Boot, you can see the equations required to figure out this number. In our case, it will be 45. The next required change is to update the vector table offset. To do so, look under the source directory, and then find a system underscore and then your board name.c file. Scroll down until you see a pound define called vector table offset. In this case, since we're using the Nucleo G0 board, we'll have to uncomment line 117. Next, we'll update the offset number to 8200U. The last change that we have to make is in the project options. If you right-click the project in Project Explorer and navigate to Properties at the bottom of the drop menu, and then within Properties under C++ Build, select Settings, and then MCU Post-Build Outputs, make sure to have the Convert to Binary file selected. Next, we'll have to enable optimization. To do so, look under MCU GCC Compiler for the Optimization tab. Under Optimization Level, select OS, Optimization for Size, and then Apply and Close, and Rebuild Index. With all these changes done, we're ready to build our application. To build the application, make sure the project is selected in the Project Explorer, and then click the Build icon. Now we've successfully built our Secure Boot FreeRTOS application. This process may differ depending on which board you're using, but just make sure to double check within the documentation that your board and your application is set up correctly. Now that we've built our firmware image, there are several ways that we can sign the image, all of which can be found in the sign directory. If we go back to our I-CUBE-ExpressLink pack, 1.0.0, projects, scripts, and then sign, you'll see the three different means by which we can sign our firmware image. KMS is an AWS service called Key Management Service, which is used to sign and encrypt and manage keys for all different encryption processes. Local, which is the one we'll be going through first, is a means by which the keys The private keys and public keys are stored locally on the developer PC. TinyHSM uses our BU5 Discovery Kit as a tiny hardware security module. First, we'll go through the local example. The pack is delivered with a private key.pem and public key.pem file. These are already stored in the pre-built Secure Boot project. So if you want to use the pre-built binaries, you must use the local means to sign your firmware. If you'd like to regenerate the public key and private key, you can follow steps prescribed in the documentation. For this video, we'll be using the pre-built binaries. As you can see, there are several files here. The one we'll be using to sign our file is the sign.powershell script. If we open it up in a text editor, we'll have to make sure that we uncomment our board, which is the Nucleo G071RB in this case, and then we'll be able to run it in a PowerShell window. The steps to open a PowerShell window in the local sign directory will be different depending on which operating system you're using. But for my case, I'm using Windows 11, so if I right-click, I can find Open in Terminal in the drop-down menu. Here, I can just type sign, and then tab to complete, and you'll see sign.ps1 comes up. I'll click enter. The script output will then be displayed in our PowerShell window. Firstly, we'll see the board name for which we've signed the firmware image for. We'll see some specifics to the signature we've just created. And then lastly, and most importantly, we'll see a Boolean value telling us whether or not the signature verification was successful. In this case, we receive true, so that means we're ready to go on to the next step. Since we're using the provided pre-built binaries and public and private key, we can now flash the binary images. To do so, we'll navigate back to our I-CUBE-ExpressLink pack, 1.0.0, projects, secure boot. We can locate the flash binary PowerShell script. We can open that in a text editor. And then make sure that we uncomment the board name that we'll be using for the project today. After that, we can save our project, return back to the directory in File Explorer, and open a terminal or PowerShell window in the directory. Here, we'll just type flash, and then tab to complete until we receive flash binary.ps1 in our terminal window. We can click enter, and this script uses STM32 Cube Programmer to flash both the Secure Boot firmware image that's delivered with the pack and our FreeRTOS Secure Boot image to the board at the correct memory addresses. Now if we navigate back to TerraTerm, edit and clear the buffer, and then reboot the device, we'll see that the board boots up. And once it connects to Wi-Fi, we'll see that the application version is again 0.9.1. Not much has changed, but now with the Secure Boot application enabled in Flash, we're able to accept host over-the-air updates. The structure to deliver a host over-the-air update is very similar and will be repeated for all different signing methods. Essentially, you have to generate a new firmware image, sign the image, and then run the host over-the-air update script. To make the desired firmware changes, we'll open up Cube IDE and make all the code changes that we'd like. Most importantly, we'll make sure to increment the firmware application version. To do so, navigate to the INC include folder in the Project Explorer. The first file should be named application-version.h. There, we must increment the application version by at least 1. So in this case, we'll increment from 0.9.1 to 0.9.2. This application version must be updated and incremented in order to accept the over-the-air update, because the Secure Boot application actually verifies that the application version of the incoming firmware is greater than the application version that is currently running on the device. Now that we've made all the changes that we'd like, we can rebuild the image, making sure that we select the application in the Project Explorer, and then clicking the build icon. Once the build is finished, we can navigate back to the I-CUBE-ExpressLink folder in File Explorer, navigate to 1.0.0, Projects, Scripts, Sign, and in this case we'll use local again. And in the local directory, we'll want to open a terminal window. From here, we'll run the sign script again by typing sign and tab to reveal sign.ps1 in the PowerShell window. We'll click enter. And now we have our updated firmware application signed with our private and public keys that are delivered with the pack. To generate the over-the-air update, we'll follow the same procedure we just did earlier on. We'll navigate back to our I-CUBE-ExpressLink pack, and under 1.0.0, Projects, Scripts, and then Host OTA, we'll open the Host OTA update.ps1 script in a text editor. We'll have to make one change here. Uncomment line 17 and comment line 16. Because we're using the Secure Boot, we won't be delivering the default FreeRTOS binary. We'll be delivering the one we just generated with our sign script, which is now called signed_binary.bin. Once we make this change, make sure to save, and then open a terminal or PowerShell window in our host OTA directory. Here we can type HOT and then tab until we find hoda_update.ps1. Click enter, and this script should create the OTA job for us again. I'll open it side by side with our TerraTerm window so we can see the script execution alongside the communication with the board. As you can see, a new host OTA update is being proposed. This is the same as before. It's now being downloaded to the ExpressLink module. Now you'll see something different. The host OTA is actually being transferred to the STM32. Upon a reboot, the Secure Boot application verifies the signature and header for the over-the-air update. Then, once the application boots in and connects to AWS, we'll see that the new application version is 0.9.2. We've now used the local sign method to successfully update our main application. And it was done with the pre-built binaries and keys provided with the I-CUBE-ExpressLink pack. Next, we'll go through the same process, but instead we'll be signing our firmware image with KMS, Key Management Service. In order to use new keys, we'll have to rebuild the secure boot image. And depending on which board that we're building the secure boot image for, they may or may not have public key infrastructure accelerators in hardware. If the board that you're using does not include PKI hardware accelerators, you'll have to download the ST cryptographic library. In my case, the G071RB does not include PKI hardware accelerators. For instance, though, boards like the BU5 Discovery Kit do. When deciding whether or not you'll have to download the cryptographic libraries, please refer to the datasheet for your microcontroller. For those of you who require the ST-cryptolib, you'll have to open your browser and navigate to st.com/x-cube-cryptolib and the X-Cube cryptolib pack can be downloaded here. You'll select Get Software and then Get Latest, accept the license agreement, and for those of you who don't have accounts, you'll have to create a my.st account, and for those of you who do, you'll just log in and register. After logging in, the download should start shortly. Feel free to pause the video here and come back once your download is complete. Once your download is complete, you'll want to open the folder where your downloads reside. The most recent download should be the ST-cryptolib. I'll extract that and I'll just extract it directly to my C drive. Again, feel free to pause the video here and come back once your extraction is fully complete. Once the extraction is complete, your C drive should open up. Navigate from your C drive to the STM32 cube expansion _crypto version 4.1.0. Navigate to middlewares and then ST and copy this folder to your clipboard. We'll then navigate back to our I-CUBE-ExpressLink pack, then into 1.0.0, projects, secure boot, the Nucleo G071RB directory, middlewares, ST, and then paste. So essentially what we've done is downloaded the cryptographic library, copied the STM32 cryptographic folder from the middleware's ST folder in the cryptographic library, and then pasted it into the secure boot middleware's folder. Now that we have the cryptolib included in our project, we can open the project in CUBE-IDE. To do so, we'll open our CUBE-IDE workspace, and then select File, Import from the drop menu, and in the pop-up window, we'll select General and Existing Projects into Workspace, and click Next. From here, we'll select Browse, we should navigate to the I-CUBE-ExpressLink pack, then 1.0.0, Projects, Secure Boot, and then the board name that you'll be using. Today, for me, of course, the Nucleo G071RB. From here, we'll press Select Folder. Make sure that the project is selected in the Projects window, and click Finish. You can now see that the Secure Boot project is imported into your Project Explorer. Next, we can generate new keys with an AWS KMS. To do so, we'll navigate back to our I-CUBE-ExpressLink directory, and then under 1.0.0, Projects, Scripts, Sign, and now KMS, we'll see several scripts here. First, we'll open the createkey.ps1 in a text editor. This script is responsible for creating the keys in your AWS subscription. As we've seen previously, we must have AWS CLI installed and our AWS CLI profiles configured. The environment variable AWS profile refers to the AWS CLI profile that we'd like to use to create our keys. Key description is an environment variable that describes the key we'll be attempting to create. If either of these would need to be changed, feel free to do so. Otherwise, we can open a terminal window in this KMS directory and run the script create key.ps1. You can see here that the AWS CLI profile is printed and the key description are printed as output. And if we navigate back to the directory, we'll see that we have a new file named key metadata with a timestamp appended to it. If we open this in a text editor, we'll see that we have all the metadata associated with the key that we just created within the script. The most important detail here is the key ID. We'll go ahead and copy this now. And open up our sign.ps1 script in a text editor. The sign.ps1 script has two environment variables as well, one of which is the board. We'll have to comment out and uncomment the board name that we'll be using in our environment. Next, we'll want to include the key ID. To do so, replace the placeholder with the key ID for the key that you just created. Once everything looks good, save, navigate back to the KMS directory or to the PowerShell window that you had open prior, and run the sign.ps1 script. Again, in the output, we get the board name for the firmware image that we've just signed. We also get the key ID printed out, as well as some specifics to our signature, and that same Boolean value telling us whether or not our signature verification was successful. Since we received true here, we're ready to proceed to the next step. When we reran the sign script, in addition to generating a new sign binary file, we also generated a new header file for the Secure Boot project. This header file is named signgen.c, and it contains the public key information for the new key that we have just created in AWS KMS. This means we'll have to rebuild the Secure Boot project. To do so, we'll make sure that the project is selected in the Project Explorer, and then we'll click the Build icon. Now that the project is built, we can flash the binaries to the board. To do so, we'll run the flash binary script again. We'll navigate back to the I-CUBE-ExpressLink pack, and under 1.0.0, Projects, Secure Boot, we can open a PowerShell terminal in this window. We've already updated the environment variables in the script, so we can run flash binary.ps1. And if we navigate back to TerraTerm and reboot the board, we'll see that the application boots and the version is 0.9.2. The difference here is that we're now booting with the keys we created in AWS KMS and verifying the signature on the application with those keys. Now we can generate an OTA with the AWS KMS keys. The structure for delivering the OTA with AWS KMS is the same as what we've done before. We'll have to navigate back into Cube IDE, and then under our free RTOS application, under the INC include folder, we'll go back to application version.h. We can make all the changes that we'd like, but the one required change for an OTA is that we increment the application firmware version. Next, we can select the project in Project Explorer and rebuild the new version. Once the image is built, we can sign it by navigating back to the I-CUBE-ExpressLink pack, 1.0.0, Projects, Scripts, Sign, and now KMS. Open a terminal or PowerShell window in this directory, and then run the sign.ps1 script with all the updated environment variables. Now we have a new signed firmware image for application version 0.9.3. So we can navigate back to the I-CUBE-ExpressLink pack, and under Projects, we'll go to Scripts again, and then Host OTA. We can use the same environment variables that we pre-configured in hoda_update.ps1. So again, we can open a PowerShell or terminal window in this directory, and run the script hoda_update.ps1. Now the script is generating the host over-the-air update, and in TerraTerm, we should see the update being proposed shortly. Again, this update is being downloaded to the ExpressLink. And then transferred from the ExpressLink to the STM32 on board. The device will then reboot, verify the firmware image with the Secure Boot application, and then boot into the new firmware application. And as you can see, we successfully updated our application version to 0.9.3 with keys from AWS KMS. We have one more signing method, which is our TinyHSM method, and we'll continue to go through that demo next. The TinyHSM signing method requires that we have a B U585I IoT02A discovery kit. This discovery kit will be used as a TinyHSM, or hardware security module, to both create and store our keys and then sign our firmware images. The first step is to disconnect your STM32 board connected to the ExpressLink. Next, you'll connect the U5 discovery kit. Provided in the I-CUBE-ExpressLink pack under 1.0.0, Projects, Scripts, Sign, and TinyHSM is a firmware image for the TinyHSM called ATU5TinyHSM.bib. We'll have to drag and drop this binary image on top of our U5 Discovery Kit directory, and this will flash the firmware required to operate the TinyHSM on board the U5 Discovery Kit. Next, we'll open the config TinyHSM PowerShell script in a text editor. The script has several environment variables that can be left as default. These are just specifics related to the certificates that you wish to provision on the TinyHSM. There are several commands that you can run, but one that must be run the first time that you configure your TinyHSM is the one in line 24. This generates both a CA certificate and a signing certificate on the TinyHSM. If you want to change anything, you can make those changes now. Otherwise, you can navigate back to the TinyHSM directory, open a PowerShell or terminal window, and run config _tinyhsm.ps1. The command in line 24 does have the debug argument enabled, so you do see a lot of the communication printed and displayed in the output. Upon termination, we've now created both a CA cert and a signing cert on our TinyHSM. Now that we have active signing certs on our TinyHSM, we can actually sign our firmware image. We can navigate back to the TinyHSM directory and open up sign.ps1 in a text editor. We just have to verify that the board name that's uncommented is the one that we're using. And once we do that, we can save. navigate back to our PowerShell window in the tinyHSM directory, and run the sign.ps1 script. Again, the debug argument is enabled by default, so we'll see a lot of the communication printed out in the display. At the end, we'll see the signing specifics, as well as that Boolean value that tells us whether or not the verification was successful. Additionally, we'll see a certificate printed out in the display. If we navigate back to the tinyHSM directory, we see the stsafe signercert.pem file. This is the cert that was used to sign our firmware image. Now that we signed our application version 0.9.3, we can disconnect our BU5 discovery kit being used as a tinyHSM and reconnect our STM32 board connect to the ExpressLink. Just as with KMS, the tinyHSM sign script also generates new header files to embed the new public keys into the secure boot application. Because of this, we have to rebuild the secure boot application. To do so, we'll navigate back into CUBE-IDE. In the Project Explorer, we'll make sure that the secure boot application is selected, and then we'll rebuild the image. Now that the image has been rebuilt, we can flash our binary images. To do so, we'll navigate back to our I-CUBE-ExpressLink pack under 1.0.0, Projects, and then Secure Boot. We'll run that flash binary.PowerShell script again. We'll open a terminal or PowerShell window and run the flash binary.ps1. Now if we take a look back in TerraTerm and reset our device, we'll see upon the reboot and the reconnect that our application version is 0.9.3. The difference is that we're now verifying the application with the keys generated on the tinyHSM module. Just as it was with KMS, it is now possible for us to deliver an OTA with binaries signed by the tinyHSM. To do so, we'll disconnect our STM32 board connected to the ExpressLink and reconnect that tinyHSM U5 discovery kit. We'll navigate back into CUBE-IDE and make all the firmware changes that we'd like to make, but especially change the application revision number, select the free RTOS application in the Project Explorer, and click Build. Navigate back to the I-CUBE-ExpressLink pack, and under 1.0.0, Projects, Scripts, Sign, and tinyHSM, we'll open a terminal or PowerShell window and run the sign.ps1 script that we configured earlier on. This script is now using the signing certificate on board the tinyHSM to sign the new application version. Once this executes, we can minimize the window and navigate to the script that will generate our host over-the-air application update. We'll go to Scripts, Host OTA, and then open a terminal or PowerShell window in this directory and run the hoda_update.ps1 script. But before we run it, we'll disconnect our U5 Discovery Kit with the TinyHSM firmware on it and reconnect our STM32 board connected to the ExpressLink. We'll reboot the board and open Terraterm side by side with the script execution. Now the update script is generating another OTA job, and we'll see it shortly in our Terraterm window once the device connects to AWS. We see that the device is currently running application version 0.9.3 and that a new host update is being proposed. Now that the image has been downloaded by the ExpressLink, it's transferred over to the STM32. Upon a reboot, the Secure Boot application verified the host over-the-air update with the keys provided by the TinyHSM, and then upon reconnecting to AWS, we can see that the application version is 0.9.4. We've now successfully executed 3 over-the-air updates, one with the local signing method, one with the KMS signing method, and one with the TinyHSM signing method. It is to be mentioned that all of these are for proof of concept. None of these is an industrial-ready security solution. Contacting a security architect is advised when delivering an industrial solution. I hope this was educational for everyone. Thank you so much.